Hello again! In my last video I talked about an esoteric programming language that I invented called Funciton. And this here is what the factorial function looked like in Funciton. And I walked you through how it works. But I also revealed to you in that video that there are only 5 basic operations in Funciton: standard input, bitwise NAND, function invocation, less than, and bit shifting. And that the language is Turing complete even with just those 5. And I challenged you to try to write an addition function, a function that will just take 2 numbers and return the sum, using only these 5 basic building blocks. If you were wondering how to do that, well, you've come to the right video. Let's think about how we did addition in elementary school. Let's take some random numbers like, I don't know, 194 plus 372. Okay, so if I want to add those numbers together, what do I do? Well, first I look at the least significant digits, the 2 and the 4, and I add them up, and I get 6. And then I look at the tens place, which in this case is a 9 and a 7. Now if I add them up, I get 16, but I'm going to write down only the 6, and then we're going to have a carry. And then when we look at the hundreds place, instead of just adding the 1 and the 3 that are there, we add the carry as well, and we get 5. So the result would be 566. But of course computers operate in binary, so let's see how we can apply that same strategy in binary. So here are some random numbers in binary. And again, we're going to look at the least significant digits first. 1 plus 0 obviously gives us a 1. And then the next digit over, we have 2 zeros, that adds up to 0. And now we have 2 1s. Now obviously when we add those up, we get 2. But we're operating in binary, so 2 is actually 1 0, which means that at this point we have a carry. The last digit of the sum, 1 0, is 0. So I'm going to put the 0 here, and then the 1 is the carry. Now in our previous example I put the carry on top and then I added it on, but I'm going to do something slightly different here. I'm going to write the carry here underneath, and I'm going to continue as if it didn't exist. You will see in a second why. So now 1 plus 0 is 1. Again, we're ignoring the carry. The 2 1s do the same as before. They give us 0 with a carry of 1. So we're going to put that 1 here. And then we have a 0 and a 1 that gives us 1. And the rest is all 0. Okay. Now let's fill in this number with zeros. So in order to actually complete the addition, what I should do now is add those 2 up, right? Because I calculated what the carry should be, and I neglected to add it, but I can still do that. So let's just do that. So again, we start at the end, and we have 1 plus 0, that gives us a 1. Then we have a 0, then we have a 0. Then we have the 2 1s here, so that gives us a 0 with another carry, which I'll put here. And we have a 0 here with a carry, and then more zeros. So again, let's fill that with zeros. And hopefully now you will see that after 3 iterations, I now have no more carries. So now I can just write down the sum just like this. And then this will be our final result. Now, how do we translate that into Funciton code? Let's think about what we actually did here. If there is a 0 and a 1 there, then we have a 1. And we also have a 0 and a 1 in the other order, and that also gives us a 1. Okay, and then of course here we have a 1 and a 0. That always gives us a 1. But if we have 2 zeros, we end up with a 0. And if we have 2 1s, we also end up with a 0. Well, there is a name for this operation. It's called the exclusive OR XOR for short. So that's what this is. This is actually A XOR B. I'm gonna say this is A and this is B. What about this number? Well, there are a lot of zeros in here, but if you remember, we placed a 1 here whenever we needed a carry, and we only needed a carry if both of the digits were 1s. So for example, here we have 2 1s. So not this one, but the next one over became a 1. So this is kind of like A and B, except that it is shifted left by 1. So it's actually that shift left 1. Well, we can just do the same thing again. So we now call this one A and this one B, and then we just recursively continue until one of the numbers is 0, which I actually neglected to show you, that this one here is of course the result of the XOR of those two numbers, but then if you calculate the AND, it will all be zeros because there are no double ones. So at that point, when the second number is 0, that's when we know that we're done and we have our final result. This is the final result. Cool, so how do we write that in Funciton code? We need to check if we are done first. So if b is equal to 0, then the result is a. But in all other cases, the result is going to be a recursive call. So we're going to call the addition function again, and the first argument is going to be this here. It's just a XOR b. And the second one is going to be this one here. So let's see how we can implement this logic in Funciton. So we're going to start by creating a declaration node for the addition function, which obviously I'm going to call plus. So let's start with the second argument, the AND followed by a shift left. So the first thing we need to do is take our two inputs, A and B, and AND them together. So let's do that. So far so good. Now we have an AND. But we want to shift left it 1. So let's use the shift left function that we've already defined. Now the other thing we need to do is XOR. So once again, just as before, I need to use T-junctions to take copies of our two inputs A and B. So let's do that. And then I'm simply just going to call the XOR function on those two. Now previously I called the function literally XOR, XOR, but I'm now going to use the hat because that is the name of the function that I've actually used in my library, because this is the notation that is used in most programming languages, or for example in C and C++, etc. So we now have our two values that we need, and now we need to add them together, right? We need to do the recursive call on the plus function. Okay, so that's looking pretty good. But there is a problem with this. I haven't actually done the if, have I? I've only done the recursive call, which means that this will be an infinite loop, an infinite recursion, and we can't live with that. So we need to somehow first check if b is equal to 0. So if you recall in my previous video, I showed you how the factorial function works. And that one has a condition like this. It had the n less than 2 condition, and we used this question mark function. I haven't shown you this function yet. That's about time I did that now. So what do we want? We want a function that takes 3 arguments. The first one is the condition, like if the condition is true. Then we want the yes value, the one that we return when the condition is true, and we want the no value when the condition is false. Now, in our case, the condition that we want is that the number is not 0. So I'm going to write the function so that it will always check if the number is 0. But how do we even select one out of 2 values? We're once again going to have to use NAND in creative ways, just like we did with the bitwise operations. So here's an interesting way of doing this. Let's say our yes value is some random binary number, and our no value is some other completely random binary number. So what happens if we take one of these numbers, like this one here, and we NAND it with zeros? Well, I think I don't need to go through every bit. You will notice that the AND is just always going to be 0, and so the NAND is just going to be all ones, which in turn gives us -1. So for any value x, if we NAND it with 0, we always get -1. Okay, now let's see what happens if we NAND a random value with -1. Now -1 consists of all 1 bits, as I've written out here. So the bitwise AND is just going to be the same as the original number, because all of the 1s are going to stay 1s and all of the 0s are going to become 0s. So the NAND is going to be the bitwise negation of this. Okay, so if we were to NAND this, all of the 0s become 1s and all of the 1s become 0s. So x NAND -1 is going to be not x. So the first thing that we want to check is that a number is actually equal to 0, which we can do by checking that it is neither less than 0 nor greater than 0. Now, since we've already written a less than function earlier, it's pretty straightforward. So I've just pasted the function in here and you can see what's going on. We're going to duplicate this value here at this t-junction and this value here at this t-junction. So this one here is going to check b less than a, and this one is going to check a less than b. And then this is the construct for OR that we had earlier. So this will calculate if either a is less than b or b is less than a, which is the same as saying a is not equal to b. Then we do another negation at the bottom to get equals. So we can put our value in there and the value 0, and we'll find out if a number is equal to 0. Easy, right? Well, let's create a little table of the possibilities. The function that compares a value to 0 is going to return either true or false. True, or -1 if it is equal to 0, or false, or 0, if it is anything other than 0. Let's call that value c. Now let's see what happens if we take any value x and we NAND it with c. So in the first case, where c is equal to -1, we are doing the same thing as this. So we end up getting the bitwise negation of x. In the other case, we're NANDing with 0, so we're doing this. We're going to get -1 no matter what x is. Let's see what happens if we NAND with the bitwise negation of c. Well, since c is either -1 or 0, the bitwise negation is going to be 0 or -1. So in the first case, we're going to be NANDing with 0. We're going to be doing this. We get -1. And in the other case, we're going to get the bitwise negation of x. Now you'll see in the first case, the value x is really only preserved in the case where c was equal to -1, which means that the input was 0. In those cases, we want the else branch, so we're just going to call that value e. In the other case, x is only preserved when c is 0, which means that the value was not 0, so we want the then branch, so let's call that one t. Now those two values I'm just going to call a and b, and now let's see what happens if we NAND those together. Turns out that in the first column here, we're NANDing the bitwise negation of e with -1, which is the same as this. So we're bitwise negating the bitwise negation. So they cancel out and we end up getting e. And in the other case, well, we're NANDing -1 with the bitwise negation of t, so that cancels out. We end up getting t. And voila, we have exactly what we wanted, right? If c is equal to -1, then the value was 0, we want the else branch, so e. And if c is equal to 0, so the input value was not 0, then we want the then branch, t. But there's one complication with this, which you may have already noticed. Let's take another look at the addition function that we tried to write. You will notice that this part of the if statement contains the recursive call, which means that we need to make sure that this doesn't get evaluated if b is equal to 0. Now, in any normal programming language, if you write if and else like this, then that is exactly what's going to happen. But since we are using calculations with NAND here, that's not going to happen, right? The interpreter would try to evaluate all of the values only to NAND them with -1. So we need some way to prevent it from doing that. Well, fortunately, Funciton actually helps us here because the NAND operation actually has short-circuit semantics in it. In a nutshell, what that means is that if you had a construct like this one here, so this t-junction here is the NAND operator, right? And let's say this function f is something that you don't want to evaluate. Well, the NAND operator will not evaluate it if the first operand, which in this case is on the right, is 0, because then the result is always going to be -1. So in this case, the NAND operator will just return -1. We want to make use of the same thing in our conditional operator. So if we think very closely about the calculations that are happening here, notice that this one here, in the case where c is 0, which is this one here, we just get -1. So this one here will not actually evaluate e. However, I said that the first operand of NAND needs to be 0 for this to work. So I'm going to have to move this over. Let's put the not c here and the t, and then make this an e, and that's a c. Let's see if we can implement this logic in Funciton. This will be our first function with 3 inputs, the condition, the then, and the else. And since they're always in counterclockwise order, this one here is going to be the condition, this one here is the else, and the one that goes down on the bottom is the true or the then. So let's start by comparing c with 0, using the equals function that we've seen before. So far, so good. Now, since we're going to need this value twice, right, we're going to need both c and not c, I'm going to use a splitter to take 2 copies of this value. There you go. Now let's start with the first one. We want to NAND this value with e, which is the else value. So that's this one here. And now let's ask whether this is the right way around. Are we doing the NAND operation in the correct order? Well, this e, I guess I can move that label over to here now. And we know that this is c. Remember that the operands are always in counterclockwise order, which means that this is actually e NAND c. So this is exactly the wrong way around. But I can fix that by just moving this line up. Okay, so now, because the output points up, that turns everything 180 degrees around. So c and e are still in the same place, but the NAND operation now considers the c to be the first operand, which is what we need. So this is actually a, which is the result of this first part. Now let's see if we can do the same with b. Eagle-eyed viewers will have noticed that we have the exact same problem here. Okay, so this one here is t, and this one here is c. I forgot to negate the c, so let's quickly do that. Okay, so we've got the not c that we need, but we still have the same problem, right? So the NAND will have the not c over here on the left, and the t value on the right, and as long as the output points down, well, this is going to be t NAND not c, which is the wrong way around. We need to turn it around. You already know the fix for this, right? The fix is to do this, but now we run into a different problem, which is that we somehow need to liberate this dangling end out of this confined box here, right? So we needed to be able to cross this wire, or literally any wire, but I'm going to be crossing this wire. So let's think about how to do that. Well, we can't just draw a cross, because we've seen earlier that if we draw a cross, then that will be a bit shift and a less than operation. We don't want that. We literally just want 2 wires to cross without their values to change. So in order to do that, we need to declare another function, and this one will be the easiest and simplest function ever. And this is it. So I've just tentatively called the function fat dot, or bullet point. I called the function bullet, Unicode character 2022, here, only to avoid a naming collision with the actual wire crossing function, which is already in the library. So as a heads up, it's actually called middle dot, which is Unicode character 00b7, and for the rest of the video, I'll be using that. It doesn't really matter what you call it, but the point is, this declaration is saying that the function has 2 inputs, right? One going to the right and one going down. And it has 2 outputs, one going to the right and one going down. And nothing else happens. So those outputs will have the same values of the inputs. That's exactly what we want. So we can easily call that function by just putting a box like this one onto this wire. I want this connected. I want this connected, and now we have our value b here and our value a here. What do we actually need? We need to NAND the 2. And there we go, this is our NAND operation. Now, since we've oriented these inputs in the way that we have, we need the output to point down. So I'm quickly going to put a little hook here so that it will actually point down. And then I can also save some space by deleting some lines. And there we go. And now we have a function called question mark that will actually evaluate only the input that we need. It will only evaluate either the then or the else. Now, just as a heads up, all of the functions that I'm writing here in this video, I've already written before, and they're already in the library that comes with the Funciton interpreter. And since I'm doing this in a kind of ad hoc way, it means that the layout of the functions is going to be quite different from what it is in the libraries, but they are functionally the same. But if you look at how I implemented the question mark function in the library, you will notice that instead of equal to 0, it will actually say not equal to. Now, why is that? Well, first of all, I can move this not box here to the other wire to maintain the same meaning. So now the function does exactly the same thing as before. Now, why would I do that? Well, let's take a quick look at how the equals and not equal functions actually look. So you will notice that the not equal to function is actually the exact same function, except for that extra not at the bottom. It's the equal to function that has the extra not, which means that if I use the not equal function, I will be doing one less operation. That's not going to be a big deal if I use the function only once or a few times in a program, but the question mark function is going to be used so many times, especially in recursive functions such as the factorial function, which you've already seen, and so this is probably going to add up, and that's why I'm using the not equal to function. So now let's come back to our addition function. We've already written the recursive part, but we still need to use the question mark function to make sure that this recursion actually terminates. Now, what is our terminating condition? Well, our terminating condition is that b equals 0. Now, the conditional function that we wrote, the question mark function, already checks for equal to 0. So I can just say if b, right? And then, of course, this will be the other way around. So if b, meaning b is not equal to 0, then we do the recursive call, else we just return a. So in order to do that, we need yet another copy of both a and b. And we know that this one here is the value a, and this one here is the value b. I'm just going to temporarily label them, which means that I can turn this here into a t-junction to take a copy of that value, and I can turn this into a t-junction as well. Okay, but now we need the a and the b to kind of meet up. Right, we need the b to go in the right side of the question mark because it's the condition, and we need the a to go on the left side of the question mark because it's the else value. So we need the b to cross this wire. So I'm just going to move this over a little bit, and then we're going to add the wire crossing function that we wrote earlier. Okay, so now all that's left to do is to add the question mark function. I'm going to put that function right here under the plus function because that is exactly where the then branch will go. So the condition branch is on the right side, so that's where b is going to go. So we're going to put the line there, and then on the left side we're going to connect up a. Now, if I'm not mistaken, and if I haven't made a mistake, then this should be a perfectly viable addition function. So let's take a look and see if it works. So here we are back with our program with the 3 and the 6 where we did the bitwise operations earlier. So this time I've put the plus in between, so hopefully we're gonna get addition out of this. But we mustn't forget that we need to turn the result into a string before we output it. So now let's see what happens if we run this program. I'm going to get an error message. Let's see if you can guess what the error is going to be. All right, let's run it. And it tells me that there is a duplicate function declaration. So the reason this is happening is, of course, I already wrote the addition function and it's called plus and it exists in the library. So I'm trying to declare another function called plus. Yeah, I can't do that. So I'm just going to have to use a different character for this function. So just for the heck of it, I'm going to use the $sign because that's a character that I know I haven't used yet. Let's see what happens if I add 3 and 6. So when we run this, we get 9. All right, let's try this with some bigger numbers. How about 111 plus 222? That should give us 333, right? Easy. Okay, let's do something, I don't know, something that does a carry. So 999 plus 222. What would that be? That would be 1221, wouldn't it? And indeed it is. What about negative numbers? We already know that Funciton can deal with negative numbers. So what if I do, for example, minus 50 and then minus, I don't know, 20? So we would expect to get negative 70, of course. And indeed we do. What about negative 50 plus 120, right? We expect this to give us 70, of course. Let's run this. Any moment now. Come on. Well, we know what the answer is, just output it. Well, it looks like it's not working. Well, it turns out that there's actually an infinite loop in here. And this is my puzzle for you. There is a problem with this addition function that only manifests itself in cases like this one. So my homework for you is figure out what that special case is and how to fix it. and then I will see you in the next video.